Okay, so we are here. We now have to group them into the stiffness matrix system. So we'll have our EI out here, EI over L. Like this. Then you have what? This one closed, and our t-test will come.
So we'll do the grouping for both equation 2 and 1 together.
Yes.
Yes.
Okay.
Here is theta 2 equal to 0. So here is 0. Here 2 is 0. Okay. So from here, the next thing that we do is we come here. All the theta ones are going to be in the first column, and theta twos are going to be in the second column, like that. So when you pick equation 1, after removing EI over L and theta 1 from it, what is left? You have R.
Yeah.
For this one, plus we've not exhausted the theta 1, so there's another one here which is plus what? When you take theta 1 and EI over L out, it's left with 4.
Yeah.
Okay.
Please, I didn't get that part well. The place where you start with.
Okay, so we are dealing with theta
Okay,
1.
let me explain to you.
Okay, sure.
Okay.
Joe, you see right now we are trying to factorize the EI out. EI over L.
Okay.
We are trying to take the EI over L out of equation 1.
Okay.
You get it? So the first, when we take EI over L, the first equation, when we take EI over L from it, it will be left with R.
Yeah, to be left with R theta.
R theta, but we have theta 1 at the last end. You see the next box, we have theta 1 there.
Yeah. Yes.
So it means that only R will be left for the first equation.
Okay.
So we put the R there. For the first part. Are you getting it?
Okay.
Now we'll come to the second part.
Okay.
When we come to the second part and we take EI over L from it, we'll be left with 4 theta 1.
Yeah.
But you see, we have theta 1 already there.
Yeah.
At the second part. So we'll be left with only 4.
Oh, okay.
You get it? So now it will be R plus 4.
Okay.
Okay.
Are you getting it?
Yes, please.
Okay.
Yeah.
So let's go to the second equation, equation 2. I said theta 1 will be for column 1. Do you get it? And theta 2 will fill column 2. So the next equation, you have 2 EI over L theta 1. So when you take this part out, this is what we factorize. What will be left is what you put here.
But there's one more component in the equation 1.
Yes, that's for theta 2, right?
Yes.
You put that one here.
Okay, so we have to finish with all the theta 1 first.
Yes, that's what we are doing.
Okay.
So we are done with this one. Do you understand? The theta 1 here, we are done taking the coefficients.
Yeah.
Okay. So from there, then we come to the equation 1 again. Right now, we are interested in theta 2. Please, do you get it?
Yes.
So theta 2 here is only this. Then we are only interested in the coefficients. We've taken the EI theta 2 over L. So it will be left with 2.
Okay.
Then when you get to equation 2, theta 2, we have from here to here. But we take them one after the other. So we take this first, and it will be left with what? 4.
Yeah.
Plus what? R. Please use it when you take this 1, 2 out.
Yeah.
So this is what we are having right now. And you are going to solve this the same way we solve.
So the equation 1, the values are supposed to be in column 1, and equation 2, the values will be in column 2.
No, not necessarily. Equation 1, within equation 1, the ones that belong to theta 1 should be in column 1.
Okay.
And in the same equation, the one that belong to theta 2 should be in column 2.
Okay.
Do you understand?
Yes.
Yes, that's how.
Okay, is the theta that determines the column where the remaining will be going.
Yes.
Okay.
Is that okay?
Yes, please.
Okay. So we move on. So from here, what we are going to do is that we are going to find the determinant of what we've just put in the matrix box. We are going to find the determinant of that and equate it to 0. So you know how we find determinant. You multiply this by this, and you subtract this by this, the multiplication of that. So because they are similar, 4 plus R, 4 plus R, what you first do is that you have to go and check whether the whole system was symmetrical. Please, you get it?
Yes, sir.
But when we checked, the system is not symmetrical. We had 2p at one end and a p at the other end. Please, you get it? We had 2p at one side and a p at one side. So here was p, and here is 2p. So it's not symmetrical. So we have to differentiate between the R's. So here you can place R1, and here you place R2. Because they are not symmetrical. So if we had them to be symmetrical, we would have maintained them like that. The R's, the R plus 4, R4 plus R, we maintain it like that. But since they are not symmetrical, you don't have to. You have to show some differences. You get it?
Yeah.
Okay. So from here, what we are going to do is we are going to have a R1. We are finding the determinant R1 plus 4. Multiplying R1 plus 4. And multiplying R2 plus 4. Please use it. Minus what? 2 times 2. The whole of this equates the whole of this towards 0. Please, okay.
So now, are you having something like difference of 2 squares?
No, it's not actually a difference of 2 squares because the arrows are different. If we had the arrows to be the same, then we could have done its difference of 2 squares. You get it?
Mm-hmm.
But right now that the arrows are different, we maintain them like that. So it's like R1 plus 4 multiplying R2 plus 4 equal to 4.
Okay.
So with this, the table that I sent to you, the stability table.
Yeah.
That's what we are going to use to find the R's.
Okay. Please, I beg again. Go over for me the last part again. The
determinant
R plus 4.
Okay.
Yes, the determinant. Yes.
Okay. So I said after having your equation like this, the next thing that you are going to do is to find your determinant of the one in the matrix bracket.
Okay.
Before you can do that, I have to first check whether the system is symmetrical.
Okay.
If the system is not symmetrical, what you do is you have to differentiate between the R's.
Okay.
So because we checked and the system wasn't symmetrical, we have to put R1 and R2. We have to differentiate between the R's.
Okay.
So that's the difference we have now.
Okay.
And from there, I said your determinant is a multiplication of the diagonals and you subtract. So this part times this part minus this times this.
So R1 plus 4. R1 plus 4 will be multiplying.
R2 plus 4.
Okay.
Hello.
Okay.
Hello.
Yeah, hello. Yeah, we are here.
Master Edward, are you saying something? Are you saying something? Can I go on?
Yes, please go on.
So from here,
yeah,
we are going to use that what do you call it? The stability table.
Okay.
So,
but the last one, the minus 2 by 2, how do we get that one too?
Minus, so it's here. You multiply this by this, then you subtract from multiplication of this by this.
Okay.
Please, are you listening?
Yes, please.
Hello.
Yeah.
Yeah, hello.
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 Yeah, hello.
Someone was disturbing. I'm not. Someone was disturbing me.
Geoffrey, can you explain it to me so that you get more understanding?
Yeah. So he's explained that when we get the R1 plus 4 into brackets R2 plus 4, we will multiply the 2 in the brackets, and then when we come to the matrix table, we will do subtraction of the multiplication of 2 by 2. That is what we have here. We will do subtraction of the 2 by 2, which we have here as 2 times 2 minus 2 times 2. Please, is that not it?
Yes. You said what? Come again. You were finding the determinants, and you know determinant is a multiplication of this diagonal. Then you subtract from the multiplication of this diagonal from it. So, but do you understand why we have the R1 and R2?
Yes, please.
Okay. So we multiplied the R1 plus 4 and then the 4 plus R2. And we subtracted the multiplication of 2 times 2 from it. And we equated it to 0.
Okay.
Did you get it?
Okay. Yes, please. Okay. I got it.
Okay. So I think that's it. And we are going to use the table. I sent it to you the last time. Mr. Edward, I sent the table to you. Do you still have it?
Yes, we have it. I think, yeah, you have it.
So this one we are going to do try and error until we get R1 and R2 to balance this to be equal to 4. But before we even go to that side, we have to establish the critical Buckling equation. The Peter whatever, Perry-Robertson or something equation. So with that equation, it is like the critical Buckling will be your P value over pi squared EI pi squared EI over L squared. Please, have you come across this equation before?
Yes, please.
So this is the load that will cause the critical buckling. That's the whole the equation we use. So this P represents the load that will cause that. And that's what we are after now. Okay. So because they are two, I'm coming. We have 2P and a P. 2P and a P. So when you replace here by 2P, you are going to get here to be 2P over pi squared EI over L squared. Please, have you gotten it?
Yes, sir.
So for the 2P load, you have 2P over what? Pi squared. The E is there, but our I was 2I. For the member that the P was acting on, the P was passing through it. Do you remember? We had here to be 2I. So here was 2P. It was passing through this. And the length was 2L, right?
Yes, please.
So 2L. So we are changing this equation to suit this. So 2P pi squared E, the I is 2I, all over what? L squared. The L is what? 2L.
2L squared.
So 2L. 2L squared. So when we simplify this, what we will get? What are we going to get? Here will be 4. And here will be 2. So the 2 here will cancel this and this to give what? 2. Is that correct?
Yes, sir.
So after everything here, it will be like reciprocation. This one will go to the top here to multiply the 2 here. I don't know whether we are getting what I'm driving at. So that here will be 2 times 2.
At the bottom side is 4.
The bottom side is 4. And it will cancel these 2 to be 2.
Okay.
Please, you get it.
Okay, then it will be left.
And this 2, because it's a denominator here, it can reciprocate here to multiply these 2 to make it 4.
Okay.
Okay, so after everything, we will be having something like 4 P over what? Pi squared EI over L squared. Please, have you gotten it? So this is 1.
So it means the two at the bottom will go to the top.
Yes, it will go to the top to multiply.
We'll multiply that. Okay.
Yes.
Okay.
Yes. So this is what you are having. So we can represent this by maybe row 1. This is that clear?
Oh, hello.
Hello.
Yeah.
Hello.
Yes, Edward.
Charlie,
Yeah, hello.
please, my network is messing up.
Oh, really?
What you feel? I didn't hear anything. No.
Eh.
Okay.
Yeah.
Okay.
That's determinant area.
Yeah.
Then Geoffrey, do it again for him.
Okay, Eddie.
Yeah.
Hello. Yeah. So from the
I'm
matrix
hearing
table. Yeah, from the matrix table, we established that R1 into bracket R1 plus 4 will multiply R2 plus 4. Then minus the multiplication of 2 and 2. So we have what you have in the square rectangular box there, R1 plus 4 into another bracket R2 plus 4, all equal to 4. So from there, he said the critical backplane load be P over pi square EI over L square will be determined. We have to manipulate that equation by the support condition, what we have on the frame. What we have on the frame,
which formula is the critical backplane formula?
This one.
That's P over
Which one?
P over pi square EI over L square.
4P over
this one.
Pi square EI or
this one.
Yes.
This one.
P over pi or
yeah,
pi square
P over pi
over
square.
L square.
Oh, okay.
Yes. And the joint we are dealing with is having 2P as the load, as the critical load, as the backplane load on it. So we try to put those details into the equation to transform the load to look like what is in the sketch.
Oh, okay.
2P, we bring the 2P into the equation, and then we do the arithmetic. We cancel the ones that can cancel, we multiply the ones that will multiply, and we come out with the 4P, and you can explain that part better for you.
Okay, so let me explain this part here.
Yeah.
Okay, so we replaced the P with 2P. Can you see it? That's the one here. Then the EI, we had the I to be 2I. So we put 2I here. And the length was 2L. So 2L will replace the L here. All squared. Do you get it?
Yeah.
After that, because the L is squared, the 2 will be squared. So you get 4.
Oh, okay.
So there will be 4 here, and there is 2 here already. So the 2 can cancel the 4, and you'll be left with 2. Do you see that?
Yeah.
And these 2, the 2 can go up here. It can climb up here to multiply this 2P for us to get 4P.
Okay.
Yes. So basically, that's what we've done. And after everything, we'll be left with this.
But I was hearing something like the stability table.
Yes. From here, from this side, you have to use the stability table to find the R1 and the R2. You get it?
So how do you find that?
Have you opened the stability table?
Hey, I'm at work. I didn't know we have class to go. So I didn't bring it.
Oh, okay. Oh.
But I printed it is in out.
Okay, I'm coming.
But if you have you use your own to explain. If I get home, I'll try it.
Yes.
Yes. That's what I'm trying to do right now.
Please, a moment. I'm attending to something right now.
Oh, okay.
But the other time, the ones that we did, it was simple.
Yes, very simple. This one is unstable. That's why you see it to be complex.
But are you sure your mom will bring something like this?
I don't really. I can't tell. I can't tell actually. I can't tell. Okay, so I'm going to share something with you, but I think when I start sharing, this one will go off.
Oh, okay.
This screen will go off. So let me see how best I can do. So I'm going to share that. Let me try and share the screen so that everybody will see it.
Okay, I'm back.
Okay, we didn't even do anything when you left, so let's all. Okay. Let me share. Can you see what I'm sharing?
Yes.
So this is the stability table.
Okay.
So what we are going to do over there, you choose your R. We are going to choose 2 different R's, and those 2 different R's. What should happen to it, bro? The 2 different R's, when you put in the equation, they should give you something closer to 4.
Okay.
Do you get what I'm saying?
That is the note.
The equation was what? 4 plus R1.
Plus, R1 plus 4.
Okay. And the second one too was like this.
R2 plus 4.
R2 plus 4. And everything should be equal to what? 4, right?
Yes.
Eddie, please, okay. I'm coming again.
Okay. So with this, Mr. Edward.
Yes, sir.
When you choose your R, the value of R, this one is try and error. So you need to try out until everything that you get here on the left-hand side will be equal to the right-hand side. Or if not perfectly.
It waste our time too.
Very, it wastes time. So here, if I choose R to be, and your R will determine your P. I don't know whether you are getting me. I
So how
didn't even,
would determine the P?
this P is like the ratio of I should have done that before we come here. You see, we had the first one that was carrying a load of 2P. We had the formula to be 4P over some pi squared something.
Pi squared EI over L2.
Yes. The one when we do for the one with a load P, we will get 2P over the same thing. Do you get it?
Oh, okay.
We didn't do that. We should have done that. But the screen has even been closed. So with this, you have to compare the two of them. The 4P over pi square something something and the 2P over pi something something. You just divide one over the other. Do you get it?
Yeah.
So when you divide one over the other, like you can name this one. You can name this one row 1 and name this one row 2. So eventually, after dividing one by the other, the one with the 2P, the one with the 2P load, and the one with the P load, it will be like, the relationship will be like I'm coming. The relationship will be like your row 1. My row 1 is representing the one with load 2P. Your row 1 will be like 2 times your row 2. I mean, you can clearly see the relationship.
So P1, the other one is equal to a 2P2.
Row 1, this is row, it's not P. I'm representing it by row. So row 1 will be 2 times row 2. It's like the effect of the one with the 2P loadings will be 2 times the one with the P loadings.
Okay.
Just that. So when you come to the stability table, it's like your R corresponds to your relationship strength, like this P, and then this P represents this relationship. So if you this row, it represents this relationship. So if my R is 4 and I have okay, let's see, my R is 3.9736. Then my row is what? 0.02. So it means that